In the last few videos, we talked about stochastic gradient descent and other variations of the stochastic gradient descent algorithm, including its adaptation to online learning. But all of those algorithms could be run on one machine, or could be run on one computer. And some machine learning problems are just too big to run on one machine. And sometimes maybe you just have so much data, you just don't ever want to run all that data through a single computer, no matter what algorithm you might use on that computer. So in this video, I'd like to talk about a different approach to large-scale machine learning called the MapReduce approach. And even though we had quite a few videos on stochastic gradient descent and going to spend relatively less time on MapReduce, don't judge the relative importance of MapReduce versus stochastic gradient descent based on the amount of time I spend on these ideas. In particular, many people will say that MapReduce is at least an equally important, and some will say an even more important idea compared to stochastic gradient descent, only it is relatively simpler to explain, which is why I'm going to spend less time on it. But using these ideas, you might be able to scale learning algorithms to even far larger problems than is possible using stochastic gradient descent. Here's the idea. Let's say we want to fit a linear regression model or a logistic regression model or some such, and let's start again with batch gradient descent. So that's our batch gradient descent learning rule. And to keep the writing on this slide tractable, I'm going to assume throughout that we have m equals 400 examples. Of course, by our standards, in terms of large-scale machine learning, m might be pretty small, and so this might be more commonly applied to problems where you have maybe closer to 400 million examples or some such. But just to make the writing on this slide simpler, I'm going to pretend we have 400 examples. So in that case, the batch gradient descent learning rule has this 1 over 400, and this sum from I equals 1 through 400 through my 400 examples here. And if m is large, then this is a computationally expensive step. So what the MapReduce idea does is the following. And I should say the MapReduce idea is due to two researchers, Jeff Dean and Sanjay Gamawat. Jeff Dean, by the way, is one of the most legendary engineers in all of Silicon Valley, and he kind of built a large fraction of the architecture or the infrastructure that all of Google runs on today. But here's the MapReduce idea. So let's say I have some training set, denoted by this box here of XY pairs, right? So X1, Y1, down to my 400 examples, XM, YM. So that's my training set with 400 training examples. In the MapReduce idea, what I'm going to do is split this training set into different subsets. And I'm going to assume for this example that I have 4 computers or 4 machines to run in parallel on my training set, which is why I'm splitting this into 4 machines. If you have 10 machines or 100 machines, then you would split your training set into 10 pieces or 100 pieces or what have you. And what the first of my 4 machines is going to do, say, is use just the first 1/4 of my training set. So we use just the first 100 training examples. And in particular, what it's going to do is look at this summation and compute that summation for just the first 100 training examples. So let me write that out. I'm going to compute a variable temp1, the superscript 1 denotes as the first machine, j equals sum from I equals 1 through 100, and then I'm going to plug in exactly that term there. So I have h theta xi minus yi times xij, right? So that's just that gradient descent term up there. And then similarly, I'm going to take the second quarter of my data and send it to my second machine. And my second machine will use training examples 101 through 200, and compute a similar variable, so of a temp2j, which is the same sum but indexed from examples 101 through 200. And similarly, machines 3 and 4 will use the third quarter and the fourth quarter of my training set. So now each machine has to sum over 100 instead of over 400 examples, and so it has to do only a quarter of the work, and thus presumably it could do it about 4 times as fast. Finally, after all these machines have done this work, I'm going to take these temp variables and put them back together. So I'm going to take these variables and send them all to a centralized master server. And what the master server will do is combine these results together. And in particular, it will update my parameters theta j according to theta j gets updated as theta j minus the learning rate alpha times 1 over 400 times temp 1j plus temp 2j plus temp 3j plus temp 4j. And of course we have to do this separately for j equals 0, up to n, where n is the number of features. So sorry about breaking this equation into multiple lines, but I hope it's clear. So what this equation is, what it's doing is exactly the same as that, where you have a centralized master server that takes the results, the temp1j, temp2j, temp3j, temp4j, and adds them up. And so of course the sum of these four things, right, that's just the sum of this plus the sum of this plus the sum of this plus the sum of that, and those four things just add up to be equal to this sum that we were originally computing in batch gradient descent. And then we have the alpha times 1 over 400, alpha times 1 over 400, and thus this is exactly equivalent to the batch gradient descent algorithm. Only instead of needing to sum over all 400 training examples on just one machine, we can instead divide up the workload on 4 machines. So here's what the general picture of the MapReduce technique looks like. We have some training sets, and if we want to parallelize across 4 machines, we're going to take the training set and split it equally, or split it as evenly as we can into 4 subsets. Then we're going to take the 4 subsets of the training data and send them to 4 different computers. And each of the 4 computers can compute a summation over just 1/4 of the training set. And then finally, each of the computers takes the results, sends them to a centralized server, which then combines the results together. So on the previous slide, in that example, the bulk of the work in gradient descent was computing the sum from I equals 1 to 400 of something. So more generally, sum from I equals 1 to m of that formula for gradient descent. And now, because each of the 4 computers can do just 1/4 of the work, potentially you can get up to a 4x speedup. In particular, if there were no network latencies and no cost of the network communication to send the data back and forth, you can potentially get up to a 4x speedup. Of course, in practice, because of network latencies, the overhead of combining the results afterwards, and other factors, in practice you get a slightly less than a 4x speedup. But nonetheless, this sort of MapReduce approach does offer us a way to process much larger data sets than is possible using a single computer. If you're thinking of applying MapReduce to some learning algorithm in order to speed this up by parallelizing the computation over different computers, the key question to ask yourself is, can your learning algorithm be expressed as a summation over the training set? And it turns out that many learning algorithms can actually be expressed as computing sums of functions over the training set. And the computational expense of running them on large data sets is because they need to sum over a very large training set. So whenever your learning algorithm can be expressed as a sum over the training set, or whenever the bulk of the work of a learning algorithm can be expressed as a sum over the training set, then MapReduce might be a good candidate for scaling your learning algorithms to very, very big data sets. Let's just look at one more example. Let's say that we want to use one of the advanced optimization algorithms, so things like LBFGS, conjugate gradient, and so on. And let's say we want to train a logistic regression learning algorithm. For that, we need to compute 2 main quantities. One is for the advanced optimization algorithms like LBFGS and conjugate gradient, we need to provide it a routine to compute the cost function of the optimization objective. And so for logistic regression, you remember that the cost function has this sort of sum over the training set again. And so if you're parallelizing over 10 machines, you would split up the training set onto 10 machines and have each of the 10 machines compute the sum of this quantity over just 1/10 of the training data. Then the other thing that the advanced optimization algorithms need is a routine to compute these partial derivative terms. And once again, these derivative terms for logistic regression can be expressed as a sum over the training set. And so once again, similar to our earlier example, you would have each machine compute that summation over just some small fraction of your training data. And finally, having computed all of these things, they could then send their results to a centralized server, which can then add up the partial sums. This corresponds to adding up those, temp I or the temp ij variables, which were computed locally on machine number I. And so the centralized server can sum these things up and get the overall cost function and get the overall partial derivative term, which you can then pass to the advanced optimization algorithm. So more broadly, by taking other learning algorithms and expressing them in sort of summation form, or by expressing them in terms of computing sums of functions over the training set, you can use the MapReduce technique to parallelize other learning algorithms as well and scale them to very large training sets. Finally, as one last comment, so far I've been discussing MapReduce algorithms as allowing you to parallelize over multiple computers, maybe multiple computers in a computer cluster or over multiple computers in a data center. It turns out that sometimes even if you have just a single computer, MapReduce can also be applicable. In particular, on many single computers now, you can have multiple processing cores. You can have multiple CPUs, and within each CPU, you can have multiple cores. And so if you have a large training set, what you can do, if say you have a computer with 4 cores, with 4 computing cores, what you can do is even on a single computer, you can split the training set into multiple pieces and send the training set to different cores within a single box, like within a single desktop computer, within a single server, and use MapReduce this way to divvy up the workload. Each of the cores can then carry out the sum over, say, 1/4 of your training set, and then they can take their partial sums and combine them in order to get the summation over the entire training set. The advantage of thinking about MapReduce this way, as parallelizing over cores within a single machine rather than parallelizing across multiple machines, is that this way you don't have to worry about network latency, because all the communication, all the sending of the temp j variables back and forth, all that happens within a single machine. And so network latency becomes much less of an issue compared to if you were using this to parallelize over different computers within a data center. Finally, one last caveat on parallelizing within a multi-core machine. Depending on the details of your implementation, if you have a multi-core machine and if you have certain numerical linear algebra libraries, it turns out that there's some numerical linear algebra libraries that can automatically parallelize their linear algebra operations across multiple cores within the machine. So if you're fortunate enough to be using one of those numerical linear algebra libraries, and certainly this does not apply to every single library, but if you're using one of those libraries, and if you have a very good vectorized implementation of a learning algorithm, sometimes you can just implement your standard learning algorithm in a vectorized fashion and not worry about parallelization, and your numerical linear algebra library could take care of some of it for you so that you don't need to implement MapReduce. But for other learning problems, taking advantage of this sort of MapReduce implementation, or using this MapReduce formalism to parallelize across cores explicitly yourself might be a good idea as well, and could let you speed up your learning algorithm. In this video, we talked about the MapReduce approach to parallelizing machine learning by taking your data and spreading them across maybe many computers in the data center. Although these ideas are applicable to parallelizing across multiple cores within a single computer as well. And today there are some good open source implementations of MapReduce. So there are many users of an open source system called Hadoop, and using either your own implementation or using someone else's open source implementation, you can use these ideas to parallelize learning algorithms and get them to run on much larger data sets than is possible using just a single machine.